on this computer. We're now recording. All right, I apologize for being slow to getting on. I was running a bunch of simulations, trying to get them done before the meeting finished, and it's still going. So, but I'm only partially through anyway. Okay, so I'm going to continue on the probability, and I'm going to try and get some understanding of how entropy works under probability. So I'm going to be doing a simple example of that, and hopefully it will get some insight into how entropy works. Okay. So we're going to be doing some simple games in here. We talked about the abstract last time. This is the 5th time. Okay. I'm going to do what hopefully is about half of the way through. I'm not nearly finished with doing what I was supposed to be done this week. I'm going to try and give you a feeling for how the entropy actually works. Now, we'll take a slight detour right now into a little bit about information theory and what Claude Shannon, who was a part of Bell Labs, developed in 1948. And he was thinking about the way in which telephone information was transferred on wires, which was various pulses, zeros and ones, along on communication lines. So he developed this whole transmission theory of information, and it turned out to be very useful in statistical mechanics and many other diverse fields of research. So if you remember back when we talked about quantum theory a couple of times, we had the contextual theory, or the context gain that we had. This is going to be similar to that, but the usual way of doing it instead of the quantum theory way of doing it. So I choose a scientist. You have to find that person using binary questions only. That is, they can only be answered that you can only ask a question that can be answered as yes or no. So since Einstein was always my ideal, I probably would choose Einstein, and you'd probably guess it if you knew me, but let's assume you didn't know me so well. There's a couple of different strategies that you could use to discover the person. For example, you could have what I consider the dumb way of doing it. You could say, is it Burbage? Is it Planck? Is it Feynman? Is it Gelman? Is it Darwin? Is it me? Is it you? Is it Bohr? And go on forever until you find out. Or you could try what I consider a smart strategy. Is it male? You generally cut half the people out if you find out that it's either male or a female. Is it alive? Was it before 1900? Is it a lot? Is he? Oh, I'm sorry, I have that in there twice. Something else was probably in there. Anyway, is he the most famous scientist ever? When you get yes on that, you can say Einstein. So these are qualified two strategies as dumb and smart. They're not uh, very specific, but I hope that you at least got the idea of what's going on with it. If you use the first strategy, you might hit upon it right on the very first question. While the smart strategy, you can't possibly win on the first question. But every time you get a right answer, it's highly likely that if you're on the dumb strategy, and if you just keep going, you're most likely to keep asking forever. The reason preferring the smart strategy is that each answer you gain more information. You exclude a large number of possibilities. Ideally, you want to set it up so that half the possibilities go with each query. Now, this is all very subjective, and I'm going to do a different version of the game that makes it more precise. So suppose a computer has chosen to put a coin in one of 8 boxes, and it can be either in heads or tails. So this is the possibilities that could be in there. You could have a tails in the first one, a tails in the second, third, etc., to the 8th, or you could have any of the heads in the same thing. So the question is, you know it's in one of those, and there are 16 possibilities. How can you figure out the answer of where this is in the minimum number of questions? Chris, are you on the line?
Yeah, yes.
Can you tell me an idea of a strategy that might be able to develop that might be able to solve this in a few number of questions?
Would you start with? Sorry, I don't really get the setup too well.
Okay, so
You want
there's
to say bisection method, right?
yeah. That who's saying?
Me, Steve.
Oh, Steve. Steve, you should
Hello.
never answer questions.
I'm sorry.
Yeah, I'm looking for other people, not you.
Okay. My bad.
Yeah. Okay, there are 8 boxes here, and any one of them could have a head or a tails. So this is the list. This could be one list. This could be a second one. This could be a third one, a fourth one, etc. So, Lukowski, if I have one of these out of here, how do I find the answer in the fewest number of questions?
Sorry, Bob, I was distracted. So you have to repeat to me what the question is again.
Okay.
Oh, I think
there's
think
six. Okay, go ahead, Chris.
would you ask, is the coin in the first 4 boxes first?
Yep, you've got it. Okay.
And then you ask the first 2, and then.
Okay, so yeah. So you've got one of the 16 possibilities here. So the first thing you do is you ask, is it left or right of the half? And that cuts it in, I say it's in the right side. Then you ask if it's up or down. Then I say it's up. You've reduced it to only two of the possibilities. And you can then ask, is it left, right again? And when I say, you know, if you say you always ask one, and if I give you no, then it goes to the other way. Either way it works for getting the information. But the next is the left, right, and then the last is heads or tails. So the sequence of questions is always to keep searching for half of the information at every time. And we have 16 possible locations, and we know that log base 2 of 16 is 4, and that's the number of questions that you can use to answer the position and heads or tails in the result. And this is the you can prove that 4 questions is all you need ever, even though there are 16 possible results. You can use 4 questions to get the position and head or tail for any of those cases. And this was all worked out in Shannon's information theory. And in our game, all of our possibilities were 1 out of 16. And in the smart questions that we just talked about, you gain the maximum possible information. This happens to be 1 bit of the total number of information that there is in there. And if you use the SMART strategy, you gain maximum information and result in the minimum number of questions. And this is a result that you can prove on average as long as you play the game many, many times. Okay, let me think about a slight other thing that's a little bit different. Suppose we have 2 coins. Each one looks absolutely identical. We can watch where they move and say which is which. And usually the way classical physicists thought about it was you would put a tiny little bit of paint, different color on each coin, and then you could always find which coin was distinguishable. And that is one way to think about it. But if they're really 10 identical coins, that is, you can't possibly distinguish between them, then if they're all in a container with a partition on the left, 5 and 5, then you take the partition out, shake the container up, and since everything is inside a container that you can't see into, when you get done, you've got 10 coins in various locations, but obviously you wouldn't be able to tell which ones were on the left to start with and which were on the right to start with. So the idea that particles are distinguishable is actually not very accurate. And although this was very foreign to classical mechanics, in classical mechanics, particles of any size could always be labeled, or at least in principle labelable. And Newton's equations of motion predict the trajectories of each specific particle in a collection. It makes that assumption. Quantum mechanics, that's not true, and it's not even possible in principle. So it will eventually give up the idea of distinguishability, even though traditional classical physics thinks about it in terms of it being distinguishable. Okay, we're going to move on to some of the games. Let's look at a 6-sided dice. You can fold this up, okay? So the top and bottom come down, the 4 and 3 go up, and the 5 goes on the other side. So when I fold it up like that and put it down, the orientation that I have is 5 is up, 2 is down, 1 is front, 6 is back, 3 is right, and 4 is left. That's the standard way in which I define dice to be. And by the way, if there's anybody has any questions, just immediately, holler. So the probabilities, assuming these are ideal cubes, that is, they're not weighted. We don't have to do any of the Bayesian learning that we talked about before. So these are not realistic cubes, they're ideal cubes. We're going to make the assumption that the probability of each die's face is 1/6. And so the probability is uniform. So suppose we have 2 die. If you put the outcomes, you could have a 1-1, a 2 and a 1, a 3 and a 1, a 4 and a 1, a 5 and a 1, a 6 and a 1, a 1 and a 2, a 1 and a 2 and a 2, a 3 and a 2, etc. So all of these could be, and if you sum these up, you get this collection: 2 and 2 3s, 3 4s, 4 5s, 6 whatever, I just lost my count, 5 6s, 6 7s, etc., and back down to 12. So the probabilities for 2 ideal cubes are the sums of the 2 die faces have probabilities that go from 1 out of what are they? They're 1 out of 6 times, I guess.
Should be 136, I would think.
1 out of 36, right? So this is 1 out of 36. This is 1 out of 36. This is 6 out of 36, or 1/6. These are 5 out of 36. I'm sorry. Yeah, 5 out of 36, 4 out of 36, etc. So this is the way it goes for 2. How about 3? Well, you can look, all of these have 1 with all of the others, then 2 with all of the others, 3 with all of the others, 4 with all of the others, 5 and 6. So obviously the probabilities of each sum is 1/216, and when you look at it, suddenly it starts looking a little bit more normalish coming along here. Okay, so taking a look at what we've been talking about, Kathleen, could you tell me what the remaining numbers of events, if we had 4 die, 5 die, 6 die, and 7 die? Kathleen?
Yeah, I don't know. I didn't follow it enough.
And you don't see the pattern.
No, it take me a while.
6 to the 1, 6 to the 2, 6 to the 3, 6 to the 4, 6 to the 5,
Okay.
6 to the 6, 6 to the 7. Okay, so you just, because there's always 6 and there's 6 possibilities with, so you keep doing the powers of them.
You have to use a calculator.
Well, I'm not worried about the numbers. I was worried only about
Power.
Oh,
6
the left
to the
side,
4,
yeah.
6 to the 5, 6 to the 6, and 6 to the 7. Okay. Miguel, what about the sequence of sums? So for 1, it goes from 1 to 6. For 2, it goes 2 to 12. For 3, it goes 3 to 18. What does it do for 4?
24.
Well, what is it, every 6? So it's 4 to the 26th?
4,
No, 24th?
4, yes, 4 to 24. And then 5 to 30.
30, yeah.
Yeah.
6 to 36.
Yep. And 7 to
42.
42, right. Okay, and the probability per event is always 1 divided by the number of events. So the answers to the question were, as I said, 6 to the 2, 3, 4, 5, 6, 7. And we worked this out, got that. And these are the same numbers over here, 1 over them. Okay, good. So if we did the probabilities versus the sequence of sums for 3, 4, 5, 6, and 7 dies, the probabilities would be the following. So for 3, you get the blue curve. For 4, you get the brown curve. For 5, you get the orange curve. For 6, you get the green curve. And for 7, you get the purple curve. So, and you can see that the 7 goes out to 42 and the green goes out to 36. So they're all exactly what we just talked about. And so the mean of all these things is basically just half of the range of possible sums. So for 3, it went from 3 to 18. So the mean is 21 divided by 2, which means there's an equal probability between 10 and 11. For the 4, you go from 4 to 24. The sum of that is 28. So this one, the exact right answer is at 14, etc. So you can find the measure of the centrality as it's called in probability, by just looking at the ranges and doing a half cross that. Okay, another test. Let's see. So, what is the best bet if you were going to figure out what the if someone took a bunch of sums and averaged them, what would be the best guess of what that would be? And we'll do it first for 3. Art. Art, are you on? Art? I guess you're not there. I have to look and find out who's the participants. Okay, Fred, what do you think is the the best bet for 3 die?
Everybody's hiding.
Okay, Steve, since you were allowed.
That's all right.
I would take the expectation value, which would be either 10 or 11.
Right.
The expectation value is 10.5, but I can't bet on that.
Right. Okay. So that was what we just talked about. And for 4 die, how about Margaret?
I don't really know. You should have called on me on the last slide. That one I knew, but this I don't know.
Okay. Well, we were just going through in the picture up here and saying that if you knew the range over which the results were between, for 3, it was 3 and 18. And for 4, it was between 4 and 24.
Okay, so that's 20 divided by 2.
Well, you add the 2 together. 4
Okay.
plus 24 gives you
28.
28. Divide by 2.
14.
14. That's the answer for 5 die. Okay. And 12 or 13 for 6, and 21 for 7, and 24 or 25 for 7. Oh, I'm sorry,
That's for 6.
Yeah, that was for 6, and this one's for 7, sorry. Okay. All right. Just want to see that people are at least getting a little bit of the idea of what's going on. All right. Why is there a best bet number for multiple die thrown together? If you think of 3 dice, there are 216 possible combinations of events. Okay, sum of 3 die. So for 3, there's only one possible way that you can get an answer, and that's 1 plus 1 plus 1. And that's 1 out of 216 possibilities. So it's not very likely. However, if we make each die distinguishable, we can make the first one blue, the second one red, and the third one white. This is next, not nest. Consider the sum of 3 equal to 5. So 5 could be 1 blue plus 1 red plus 3 white. Or it could be 1 red plus 1 white plus 3 blue. Or it could be 1 white plus 1 blue plus 3 red. Could be one, or that's one way of getting 5. Another way is getting 1 blue, 2 red, and 2 white. Again, permuting the colors, we have 1 red, 2 white, 2 blue. Doing it again, 1 white, 2 blue, 2 red. So all of the different ways in which you can get the same number under different ones counts for a possible sum equal to the same number. These are what I am going to call as mu C events, and identical with uniform probability. And the ones that make up the sums, I'm going to call are MC events. And for now, that's just labels. Later, I'll talk about why I chose those labels. Now, those are not identical. The sums go, in the case of 3, between 3 and 18. And the probabilities are not the same. They're not uniform probabilities on the case of the sums. So when we went way back to only 2 die together, the MC sum equals 7 happened most frequently, that is 6 times versus the next largest at 5. And this type of a thing happens for any sum or MC event. So because MC events have non-uniform probabilities, there's also always going to be at least 1 or 2 events that will have some maximum probability associated with them. That's what we just looked at. Everybody following what I'm saying so far?
Yeah.
Okay.
Okay, great. So the naming that I'm using for these types of events are later going to be in our description of entropy. So let's remap the numbers on our cube. We had this, which we folded up and down, and then we folded the other way and we folded around. So now I've got 0, 1, 1, 0, 0 in here. And
it doesn't matter. The cube is still cube.
So our new standard faces are, the old face was 5, the new face is 0. The old face was 2, the new place is 1. The old one was a 1, it has a 0. It was a 6, it has a 1. 3, it has a 0. And 4, it has a 1. So now I've got a die that I can flip, and it's either going to, whatever comes up is either going to be a 0 or a 1. And we're going to start about games having initially 10 dice, all with the identical orientation. So all of them will be 0 up. All of the front ones will have 1, and the white one will have 0. And at some point later, I'm going to change the version of the game with random initial settings of the dice, but for the start, we're only going to be dealing with initial sets of all 0. So all identical orientations. So what are the rules of the game? First, a random die is chosen. So if there are 10, one of the, let's say the 7th one was chosen, then you can pick it up and you can choose equally likelihood of rotations. And there are 3 types of rotations. You can have a rotation in the XY plane, you can have a rotation in the XZ plane, or a rotation in the YZ plane. And so we have a way to be able to understand where everyone has gone to everything whenever we've done any of these rotations. And each of the rotations will be done a discrete number of times, again, equally likelihood of 0, 1, 2, or 3 times pi over 2. So that will let us give a system, which we're calling, again, another mu-c system. And the sum of the up faces is going to be the MC system.
Quick question.
Yeah.
I've never thought about this kind of game, but even though it's just 0 and 1s on the faces, the way you map them from the 1 to 6 dice, there is a unique position for each one. In other words, even that it is, once I looked at the dice, I could identify which of the 6 locations, which of the 6 positions you possibly had. I could map it back to 1 to 6, even though it's 0s and 1s.
Right.
Got it. Okay.
That was the point.
Yeah. Right.
So all of the various rotations are actually permutations of the original 1 to 6, and then you just take whatever that permutation is and you map it into the 0s and 1s that we had in our original mapping.
Neat. Very interesting. Like it. Thank you.
Yeah. So, okay. And right now I'm starting with 10 of these things, thinking about it. Okay, I'm gonna go back and just to make it easier to do some of the computations of what we're going to be doing, I'm gonna show a simpler case, but we'll eventually go to 10 and 100 and etc. So if we had only 4 dice and we were looking to find out what sum to 2, these would be the possibilities. You could have one a 0, one a 0, the second one a 0, the third a 1, and the fourth a 1, or the first a 0, the second a 1, third a 0, fourth a 1, first a 0, second a 1, third a 1, then a 0. You could have the first a 1, second a 0, third, fourth, etc. So there are 5 possible ways in which I obviously, no, 6. I got it right. I had it right. Sorry. Okay, 6 of these that are there. So if we start with 5 dice, and we do the events, the sums from 0 to 5, because there can be all zeros, or at 5, they can all be 1s. But for 1, there's 5 of these that have a 1 in one of the positions. And for the 4 is the complement of the 1. Does everybody know what the complement of a set of bits is?
Yeah.
Okay, yeah, complement just changes the zeros to 1s and 1s to 0. So each one of these is a complement of the corresponding one up there. And similarly, there can be a 2 and a 3. There are 5 1s, there are 10 2s, 10 3s, and 4 5s, and only 1 5 and 1 0. So
Well,
let's, yeah?
on your last slide, you did something more than just change the 1 to a 0. If you look at it, you did something more than just change 1s to 0s and backwards.
Well,
to get-
I reversed them.
Well,
Or I did them in a different, I did this all on a computer, so I didn't check to see that there are complements.
but
So for this one, yeah, this one is complement to that one. This one is complement to this one. This one is complement to that one. So they're all cross is the problem. Right. You're right.
okay.
I did this all on a computer and did not. I knew the answers were right. I just didn't check to see where they were. Okay. So suppose we do our 5 dice and we do them for 200 steps. We can do multiple runs, and I've done 2 here. You can see that they behave somewhat differently. They don't look exactly the same, certainly. They're all random sets of runs. But they all tend to stay around the 2.5 level, whether it's here or here. But for a small number of die, they're going to go sometimes they'll go all the way up to the 5, and other times they'll go all the way down to the 0, as in these places. So let's take a look at more die. As I said, they tend to bounce around the mean, roughly 2.5, and but they can go well above it and also pretty low. So what happens if we, what am I doing here? Okay, from our previous bits of possible, we know that the mu-c events are equiprobable, and so it's equally likely to go up from 3 to 2, and half as likely to go up from 3 to 4. If you take a look at the outcomes here, there are 5 equiprobable ways of getting down from there are 10 of these and 5 of these. So it's much more likely that you're going to go up to a 3 than you're going to go down to a 1. And you're much more likely to go down to a 2 than you are to go up to a 4. And that's the reason why these they tend to stay in the region around the mean. So let's double the number of dice. So now we've now got 10 dice, and we'll do another 2 runs, and this time we're going to do 500 at a time. Now for the second run, they do go all the way up to 10, and they do come all the way down to twice, but not very frequently. And on the first run, except for the initial conditions, they never go up to 10 and they never come down. So they tend to seem to stay closer to the mean as we have more dice. So we'll try using even more dice. So if we have 10 times as many dice, that is 100 of them, and we have 1,000 steps, then the first run, it takes almost 500 to get to the mean, and it stays pretty close as we keep going. In the second run, they go up a little quicker, but they still stay very close to.
Bob, I have a question.
Yeah.
Where is that initial part of that graph coming from? I see it starting from 0 and working its way up to 50.
Yeah, it's the initial conditions. I start every set with the dice always in exactly the same positions.
Oh, okay. So you're not randomly throwing the dice to begin with.
Right.
You're
Right.
starting from
Right.
what you showed before. Okay.
Right. I'm next week's lecture, because I didn't get as much done here as I wanted to. I'm gonna show the same thing with randomized initial conditions.
Okay.
And you'll get a similar kind of behavior, but you'll start from a different initial condition.
I
So
have a question. Oh,
Okay.
Yeah.
are you finished, Steve?
Well, I just want a follow-up on what Bob said. I thought, and I'm obviously wrong, each run I thought was a random toss. Is that?
Well, the way in which I did it was you choose one of the 100 dice.
Okay.
Then you choose randomly between 1 and 3 whether you're going to do an XY rotation or a YZ rotation or an XZ rotation.
Okay, so you're working on just one die for each.
On each step, yes.
Okay, that is clear.
And then, so that's why it takes so long to get up here. Since you're only doing one, you know, and you've got 100 die, it takes a long time before you.
Yeah. Well, now that makes sense.
Okay. Good.
Okay. My question is, a few slides back or whatever, you said there's I think it was pretty significant. Oh yeah, no, that the one with the text on it, not the numbers. Oh, anyhow, no, no. There. I think that's the one. No, that's not the one. Anyhow, I don't think that's the one, but in one way or another, there was no, there's a significantly higher chance of going from a 3 to a 2 than there is from a 3 to a 4. Wherever the
That's
heck
there.
that was.
That right here.
Okay.
So if you go
There was a
from,
text about it. There was a text about it. Here's my question. It doesn't matter which slide you show. Why is that? If you're only
well,
going
if you're
1 off of the mean, what's the
No.
difference whether it goes up or down?
well, if you're in A3 and you choose one of them on here, any one of these, it is more likely to get into the 2s, which there are 10 possibilities, as opposed to going up to the 5 possibilities of 4.
Oh,
Okay, so there's 10 possibilities here, 10 possibilities here, but only 5 here. So it's more likely that you're going to get one of these than you're going to get this, one of these.
okay.
Okay, and
Mhm.
similarly, if you're here, you're more likely to go to this one, the 3, than you are to go down to the 1.
Yes.
Okay, that was all I was talking about.
Okay.
Okay. And this is the one where my computer crapped out and I was doing 10,000 dice and 100,000 steps. And unfortunately, it did something wrong and I haven't figured out what it was, which I was computing just before I was doing the slides here. So unfortunately, I don't have a picture to get that. I will get it done before I put out the lecture, but I don't have the picture right now. So let's stop and think a little bit about what it is we've discovered so far. So what is this thing that changes at each step? I've mysteriously called them MC events. And if you would give a name for them, a name that reflects what you were learning about from these games, I'd appreciate anybody giving some recommendations.
Well, what changes is the sum, right?
Yep. It's a sum
The
over
state?
a large collection of equiprobable events.
The state of the system.
Well, yeah, this is
It's the odds.
well, it's not the odds, but it is.
The state.
It's the state, right? So there is a huge collection of possible events. Now, when we were talking only about 5, whoops, here we had 20, 30, 32 possible what I've called MC events. And each one was a collection of 5 MUSI events. And
Well, now if MC is the sum, then I wouldn't call that a state, because the state to me is the specification of what each one of those is reading. Now, when you tell me
Well,
what the sum is, I don't know what each one is doing. I just know what the sum is.
right, right. But the collection of muses, all of these individual items, are what I'm trying to think of as micro uh, canonical ensembles. So the collection of all of these here would be the collection of all the microcanonical ensemble,
Maybe call that the microstate,
the
and the
microstate,
MC
MC
and the
stands,
capital MC would be the macrostate.
right. That's the other idea. So you do some type of coarse graining. In this case, we sum over all of these states, and those become our macro canonical states. So this is a idea of how you do coarse graining, how you do micro canonical ensembles, and how you get macro canonical ensembles.
Bob, would you explain the word canonical to us?
It was a name that was, I'm not sure I know why it was used. Steve, what's the reason canonical was used?
I'm with you. I thought it was a historical situation. It was given that name, but I can't tell you exactly why, unless it's some Pope-given ex cathedra sort of thing. But no, I can't tell you why.
Yeah,
It's related to canon law, I think. You know, the absolute truth or something like that.
well, the macro canonical
Wait,
event
can I ask
is
a question?
anyway. Sorry, who's got a question?
I have a question. Has this got something to do with length, depth, and width? Are they related?
No,
They are to me.
no, they have
Because
nothing
I
to
don't
do.
understand. Remember, I don't understand numbers. So I'm coming at it from a thinking point of view.
No, you have to think about this as events
We
that are
only-
happening and the probabilities of the events happening.
What I'm saying is we only think in 3 dimensions when you're not in math. And if you think in 3 dimensions, this has to be related to length, depth, and width only.
No,
because we
no,
can't go any.
no.
Now we have added space.
No,
So
this has to
okay.
do.
I give up. I can't ask this question because I can't really understand.
If we were talking about the physics of this, we'd be talking in the case of 5 particles in a gas. Each one of those particles would have an X, Y, and Z, a momentum in X, a momentum in Y, and a momentum in Z. So 6 numbers for each particle times 5 particles. This would be a 30-dimensional space.
Yes, has to do with dimension then. It does have.
It has to do with dimension, but it has nothing to do with length.
Well, that's part of dimension. I've got to discontinue my discussion because I really don't understand.
Well, what you need to think about is collections of things happening. that we're working towards the idea of getting to atoms moving around in volumes, and they have positions and they have momentum. That's 6 numbers for each particle, and typically in a volume of gas there would be 10 to the 24th of those particles. So we're talking about a 6 times 10 to the 24th dimensional volume space. We're thinking we're looking at really large things that are happening.
Yes, I
Things
know.
that make them very hard to think about. So that's why we're trying with 5s and then 10s and 100 and 1,000, 10,000, to get our thinking about how it works on the way up to there. Am I going in the wrong direction? I think I'm going in the wrong direction. Okay, back to where I was.
Now you're there.
Okay. So, yeah. So how does we've sort of learned that if you start with a very specific microcanonical ensemble, and you choose one of those, a very low valued one, and then you just keep changing them one at a time, and eventually they'll go up close to the equilibrium level. So we've also learned that they don't move very much up and down around that place. So how does this occur? This is the great insight that Boltzmann had on the H theorem.
So it's a question of probability, right?
Yeah, yeah. So you can, okay. So why does the change always occur in one direction towards the equilibrium line? Although Steve just asked about that question before, and I partially answered it.
I would venture a guess. First of all, somebody's talking in the background and they need to mute themselves.
Right.
Whoever it is. Anyhow, yeah, I agree with Steve. It's probability, and just as you showed in that table when I asked the last question, there are more chances toward the equilibrium line than there are. However, where does it say here, and why it never goes back to the initial configuration? And I would say that given enough throws of the dice, 100 billion, a zillion, a godzillion, whatever, one time it'll hit that initial configuration because it's a bell-shaped curve. So sometime it'll do it.
Yeah,
Right.
I think Miguel is right. I think the never and always
are in quotes because
are incorrect. Yeah.
Okay.
Yes,
Oh,
there
it is in quotes, so sorry.
It's in quotes, and the reason it's in quotes is because Poincaré showed that eventually you can, if you do enough steps, you will get as close to the initial condition as you want, even with 10 to the 24th particles. So never is not correct. But in terms of, you know, the times we're talking about much, much longer than the time that we'll get heat death in the universe, which is a long, long time. So anyway, yeah, these are in quotes because they're not accurate. You will eventually go back to the initial condition, and you will eventually also not stay close to it forever. You will, you know, you will eventually go back, and you will go eventually up all the way to the top. You will eventually get everything, but that eventually is so long. It's just an amazing amount of time that you can't even begin to think about. All right, and sorry,
Quick question.
Yeah.
Yeah, the way there's interesting bit of information. You know, you were talking about, you started from this low state, the 000 state, and the amount of time it took you to get to equilibrium probably is some indication of you know, how long it might eventually take you to get back down.
Actually, much longer than that amount of time.
Well, but still, because you can only make these incremental changes. You know, the changes, at least in this simulation, are one number at a time. It's always got to be one number at a time. But at least that gives you some indication of, look how long it took you to even get there. So you can only imagine how long it would take you to get back down.
Right. No, but it's much long. This, you know, took almost half the amount of steps that I had. Believe me, it'll take many more than half the number of steps. You know, if I ran this for a few billion, I still wouldn't get back to the initial condition.
Oh, no, I wasn't implying that. I'm just saying it is interesting to see even how long it took just to get there, to show you how long it would actually take to get back down. It would be, you know, obviously the probability is so different. The probability of getting up there was pretty low, you were assured of getting close to that average, but it even then still took half the amount of time just to get up to average.
But that's a function, I think, of the rules of the game. If you were to just roll all of the die randomly, you'd get up to that equilibrium very quickly, probably in 1 or 2 tosses.
Yeah, no, I agree.
Yeah. No, it was the nature of the game, and I'm gonna show a few more games next time. But the basic idea is to realize that all of these collections of small events are what are called the microcanonical ensemble, and they are all the possible ways in which they could all occur. And when you do some kind of coarse graining, which here I've simply summed over all of the values, those make up what's called the macrocanonical ensemble. And so that was the point of this game, was to think about those, and the fact that you can look at very coarse grained, very crude sets of numbers, and you'll eventually still get very good results statistically there. And the other thing that eventually I hope people will be able to realize is that the learning is about the gaining, or the missing information. You have a certain initial state of information. You keep changing your state of information, and you only know crude measurements about it, the coarse graining, and still you can get all of these really good understandings of how statistical mechanics gives to this. So I apologize. I just didn't have time this week to put enough together. So I will add a few more slides onto this and send it out with the slides, and then continue again next week. Any questions?
Well, thank you, Bob. That looks like you've done quite a bit of work as it is.
Well, not nearly as much as I wanted to. Anyway.
Yeah.
I do actually have one final question, or maybe it's final, who knows? But the change from a real die to the die where three of them are zeros and three of them are ones. I'm thinking that the purpose is to simply simplify the vast amount of numbers that we're dealing with, because I think what you've done in making a six-sided figure into zeros and ones, equal zeros and equal ones, is try to represent three-dimensionally with a solid object a two-sided figure.
Actually, I was trying to deal with a six-dimensional object, because in phase space, you have, for each entity, you have three spatial components and three momentum components. So every particle has six components associated with it. So I was trying to mimic the way in which phase space operates in the game that we're dealing here, because every particle would have a six-dimensional number, six set of numbers associated with it. Did
So,
that
Bob,
make sense?
Well, I understand what you're saying.
Yeah.
I'm not sure if that addresses exactly what I'm saying, but I mean, basically, you know, when you have a six-sided figure with three zeros and three ones,
Oh,
and
that was,
you don't designate which one of the ones came up. I mean, there are three possibilities. So the only thing that matters is that a one came up, as opposed to a blue one, a red one, or a green one.
well, that's actually not the way in which the process works, because you have the cube in a particular orientation. So it's in the orientation that I showed for the, whoops, for the cube. Let me see if I go back here. So in the cube that I had way back in the beginning, there it is. All right, so 5 goes up, 2 goes down, 1 goes front towards you, 6 goes away from you, 3 is to the right, and 4 is to the left. Everyone is in that orientation.
So
What
it's
I do is I take it and I choose one of 3 possible planes. So you can put an X, Y, Z on this dice, and you can either do in the XY plane, or you can do in the XZ plane, or you can do in the YZ plane. So I choose one of those 3 planes equally. And then I rotate between 0, 1, 2, or 3 pi over 2 rotations. So I always change it into a particular place. So I've always moved the state of the die to some particular permutation of the original one. And then after I've done that, I map each of the numbers again back into the zeros and ones that I showed. Where is it? Oh, I'm going the wrong way. Sorry. Where is it? Ah, yeah. So I have the mapping now. So I've taken the 6 numbers, moved them into a permutation because of the rotations and orientations that I've used. Then I take the numbers and I map them back into the same ones and zeros. And then I know what's at the top of the cube. I know what number it was on these 6 numbers. And then I know what it was, either a 1 or a 0 at the end of the process. So that there is no, all of the processes are physically unique. And they're checked and they're tracked on each cube.
Oh, I see what you're saying. In other words, if a 1 comes up, you know which of the ones came of those.
Exactly.
Because yes, I see that.
I keep all of these numbers in the thing, and I do the changes that I said, and then that gives me a different form of these numbers. Now I map these back into the same ones, and I know which one's on top of the cube, which one maps into it. So I don't lose any information.
So what is the purpose of changing to zeros and ones?
Simply to make the summing a whole lot easier.
That's what I thought. In other words, you're not having to deal with as astronomical numbers as you would if you kept them original.
Right.
Okay.
Exactly.
Yeah.
Exactly. So, but in terms of the process is
the same.
It's physical. It's exactly the way in which a real atom would go through particles. You know, you have Newton's laws that tells you where it's going to go. It's going to go exactly to a certain place and a certain momentum. And the same thing happens here with the cube. The rotations of in the different planes will tell you what the orientation of the cube is. Then you map it back into zeros and ones, and you know the ones on top, and it tells you whether it's a 0 or a 1.
Okay.
And you keep each one in the, you keep the 6 numbers for each of the 100 or 1,000 or 10,000 die, and you do all that manipulation in order to make sure that nothing is happening randomly. It's all happening, deterministically, the same way that it's Laplace's clockwork universe. I'm not randomizing things. I'm actually physically moving things around. And of course, the results still wind up giving you very probabilistically looking numbers. Okay, well, I think that's about all I can give right now. And I hope I'm gonna stop the recording now.
Hey,